In this chapter, we will go over how to write a balanced chemical reaction, the types of reactions, and how to use stoichiometry to determine the number of moles in the reactants and products. And at the end of the chapter, we will go over calculations for the limiting reagent. So, whenever we want to talk about chemical reactions normally are represented by an equation. And the equation has two sides, a reactant side and a product side. So the reactants normally are substances that undergo a chemical change in the reaction. Reactants are written on the left side of the arrow that points towards the product. So the reactants are written over here. Normally, reactions are made up of either one reactant or more than one reactant. So if you're using more than one reactant, then we're going to use a plus sign between them. Products, on the other side, these are substances that are produced as a result of the reaction taking place. So when the two reactants react with each other, or when one reactant decomposes, you are going to go ahead and get the product. Products are written to the right side of the arrow, so they are written here. And sometimes we form one product, sometimes we form more than one product. So if you form more than one product, we're gonna write a plus sign in between the products. Let's have an example over here. So in this reaction, we are using two hydrogen. We are using two hydrogen atoms in this case, and they are reacted with an oxygen gas. So a hydrogen gas is reacted with an oxygen gas in there. So these two are considered to be reactants. Okay, and those two react with each other and they make two water molecules. So we are going with the hydrogen gas, oxygen gas. We agreed last time that hydrogen is an element, right? It's made up of the same element, which is hydrogen. It's two hydrogens. So it is a diatom. Oxygen is a diatom. Hydrogen and oxygen are two gases. These two gases, they react with each other and they form a completely different substance. So this is a chemical reaction. This is called a chemical reaction. And the type of change here is the chemical change. You're going to form your product in this case. Okay. And as you can notice over here, the symbols are different. We're going from a gas state into a liquid state. So the symbol normally that is written in parentheses to the right of each reactant and product, it represents the state of the substance that exists. So G stands for gas. So here I do have a hydrogen gas reacting with an oxygen gas to form water, which is a liquid. So L represents a liquid. And if you have a solid, then we're going to represent it by an S. Now, substances that are dissolved in water, normally we don't represent them as a liquid. These are solids that are solvated in water, so we represent them as aqueous. And AQ stands for aqueous. So AQ over here stands for aqueous. Okay, so let's have an example. If you have a solid sugar and if you have water, sugar is a solid and it has this molecular formula. Remember, when you draw a molecular formula, when you write a molecular formula, you have to show the number of atoms that molecule have. And here I do have 12 carbons, 22 hydrogens, and 11 oxygens in there. When you write the molecular formula, you have to arrange the atoms by increasing electronegativity. So you start from the least electronegative to the most electronegative. Guys, hydrogens always come after the carbon. So you draw the carbon, hydrogen, and then the oxygen. You have the electronegativity table, you can follow that. So once I dissolve the sugar in the water, I am not changing the composition of the sugar. It's still sugar, you know, but now the sugar is solvated in water. It is dissolved in water. So to represent the sugar dissolving in water, it's going to be in an aqueous state. So now the sugar is an AQ. Okay, so over here, this is the reaction. This is called a simple reaction, simple dissolution reaction, where I am showing the sugar being a solid. It's added to the water that is liquid, and the sugar now is dissolved in the water. Notice I did not change the sugar, so I started with sugar, I ended up with sugar. So this is not a chemical change. This is going to be a physical change where I'm changing the state of the solid, or the state of the matter, let's say, from solid to aqueous. Let's have examples of chemical change reactions. Chemical change reactions is when you start with something and you end up with completely something else. So see here, I'm starting with zinc. I'm reacting it with an acid, which is HCl, hydrochloric acid, and I am forming zinc chloride and hydrogen. The products are completely different than the reactants. So you can easily see that this is a chemical reaction. Same thing here. I'm starting with ammonium nitrate, or nitrite actually, ammonium nitrite, and I'm reacting it with nitrogen. So I'm forming an oxygen and water. So again, I'm forming completely different products than what I start with. So this is going to be a chemical change reaction. Now, chemical reactions, whenever you want to represent them in an equation, you want to make sure to balance the equation. Why is that? Because balancing chemical equations follow the law of conservation of matter. And the law of conservation of matter states that during a course of chemical or physical change, the total mass of the products remain equal to the total mass of the reactant. So whatever you start with should have the same mass as your product in there. In other words, if you have a hydrogen, if you're starting with your reactants and your reactants have a hydrogen atom in there, the hydrogen atom is not going to be destroyed. It's going to change its form and become something else, but it's still going to be a hydrogen in there. So this is called the law of conservation of matter. So the total mass of the products always remain equal to the total mass of the reactants. Whatever elements you start with, let's put it this way, whatever elements you start with in the reactants, you are going to get them in the product, but in a different form. So the hydrogen is not going to be lost. It's going to, there you will have a hydrogen in the product, but it's going to be in a different form. If you have an oxygen in your reactant, again, you're going to have an oxygen in your product, but it's going to be a different form. Instead of being an oxygen gas, now it's going to be part of the atom for the water molecule. Whatever you start with as a mass, you should end up getting it as a mass. Okay. So for these reactions in there, we want to make sure that the number of atoms that we start with is the same as what we end up with. For example, for this reaction, I'm starting with 4 hydrogen atoms. Okay, the two that you see over here is part of balancing the chemical equation. See the one that you see in there? Again, it is part of balancing the chemical equation and part of balancing the chemical equation. So you're reacting 4 hydrogen atoms with 2 oxygen atoms. Why did I say 2 oxygen atoms? Because here I have O2, which is a diatom, right? So this over here is going to be 2 oxygens, so that's why it's a 2 oxygen atom in there. So in my product, I am expecting to get the same number of atoms. I'm expecting to get 4 hydrogen atoms and 2 oxygen atoms. So this is why I put my numbers in there, just to make sure to balance the equation. So what are the steps of balancing the chemical equation? It's really straightforward. You just need to follow the steps. So the first step there, you have to balance all the elements and keep the hydrogen and the oxygen till the end. Don't bother with them. Do not bother with them until at the end. Now, once you balance all the elements except the hydrogen and the oxygen, guys, balance the hydrogen before the oxygen. So you keep the oxygen until at the end, and then once you are left with the oxygen, you go ahead and you balance that. Let's have an example. So in this one, here I'm starting with a methane. What is a methane? A methane is a hydrocarbon. So methane is a hydrocarbon. Hydro stands for hydrogen and carbon stands for carbon. So it's a compound which is made up of hydrogens and carbon. So we call it a hydrocarbon. So this hydrocarbon, as I see in this chemical reaction, I called it a chemical reaction because I'm starting with reactants and I'm ending up with different products. So with this chemical reaction in here, I am reacting methane with oxygen. Oxygen is a fuel, okay? So in this case, what I am doing is I am burning the hydrocarbon. This is what I am doing. So this reaction here, we are going to call it a combustion reaction. And for combustion reactions, our product is going to be, for this type of reaction, carbon dioxide and water. It's always going to be carbon dioxide and water. So now here we want to balance that equation. If you can see, the equation is not balanced because the number of carbons here, you start with carbons. Carbons are the same, true. For the hydrogens, you have 4 hydrogens here. You do have 2 hydrogens there, so hydrogens are not balanced. And then the oxygens, I have 3 oxygens in the product and I have 2 oxygen in the reactants. So again, the oxygen is not balanced. So I need to balance this chemical equation. For this particular one, there is a general combustion equation that normally we follow for this type of reaction. And it makes it easy because sometimes the hydrocarbon contains a lot of carbons in there. So it makes it easy whenever you want to go ahead and balance it. So let's write it down. The general combustion equation. And the general combustion equation goes with the number of carbons in there. So if I start with, and this is called a hydrocarbon alkane, okay, plus 2. So if I'm starting with an alkane, methane is an alkane. So any hydrocarbon that follows this molecular formula in here, where N is the number of carbons. So if I want to go ahead and apply it to here, N is equal to 1, right? Because you have 1 carbon. So the H here is going to be 2 times 1 plus 2, so it's going to be 4. So this is as if I'm saying it's a CH4. So this is the same as that. Any hydrocarbon that has this molecular formula, you can go with this combustion equation that I'm just going to write down in order to balance it, and this will make things easier for you. So you react alkane with oxygen, and the coefficient for the oxygen is a 3n plus 1 divided by 2. You're always going to get carbon dioxide and you're always going to get water. So the coefficient for the carbon dioxide is n, which is the same as the number of carbons. And the coefficient of the water is n plus 1 in there. So the number of carbons plus 1. So to balance that, if I want to use this equation over here, then I'm going to start with the hydrocarbon. I'm going to react this hydrocarbon with 3n plus 1. So it's going to be 3. The number of carbons is 1 plus 1 divided by 2 in this case. So that is going to be 4 over 2. So it's going to be 2. So now my coefficient for the oxygen is going to be 2. And that is going to give me N carbon dioxide. N carbon dioxide, I do have here 1 carbon, right? So that is going to be just 1 carbon. Just skip the 1. You don't have to write down the 1 over here. And then N plus 1 water. So the number of carbon is 1, right? So 1 plus 1, that is equal to 2. I can follow this combustion equation, or if you decide you don't want to follow it, it's fine. What you need to do is just to start by balancing the carbons first. So carbon is 1, and then move to the hydrogen imbalance. So here I have 4 hydrogens. Here I have 2 hydrogens there, so I need to put 2 in front of the water. So now it's 4 hydrogens, and then at the end I count the number of oxygens. I have 2 oxygens here, I have 2 oxygens there, so this is 4 oxygens, then definitely I need to put a coefficient in there. Okay, So this is how you balance a chemical reaction. And in this particular case, it's called a combustion reaction. Let's have more examples. You can have a lot of different types of chemical reactions other than combustion reaction. Here, this is an example of an acid-base reaction. You don't need to know the type of the reaction to balance the equation. So with these, I'm going to start with everything except the hydrogen and the oxygen. So you can start with either the sodium or you can start with the chlorine, guys, whatever you want. So I'm just going to go ahead and start with the sodium in there and see, like, I'm starting with the sodium here, sodium there, I'm good. So the sodium is balanced. And then I go to the chlorine. So the chlorine in there, I have one chlorine, I have one chlorine. I'm fine with the chlorine. And then you look at your hydrogens and then oxygen at the end. So I have two hydrogens in there. See, one, two. So this is the two hydrogens, and then the oxygen. So I would say, okay, my equation is balanced. So this one is a balanced equation. I'm good. Over here, I can see it's not a balanced equation because the magnesium is balanced, but the oxygen here, it's 2. This one is 1. So all I need to do is come to the side and write 2 there. This made my oxygen having 2 atoms, right? But about the magnesium there, the magnesium is also 2. And now it's not balanced in the reactants. So I need to balance it. And here you go. This is 2. Sodium carbonate gives me sodium oxide plus carbon dioxide. So I'm starting with the sodium. The sodium is balanced. Na2, Na2, I'm good. Do the carbon. Carbon is balanced. I am good. Okay. And then um, and then what I have over here is the oxygen. Oxygen is 3, oxygen is 3. So I am fine. So this reaction is balanced in there. Um, Another example, magnesium. I'm reacting it with an acid, and then I'm gonna get magnesium chloride and hydrogen. So I'm starting with the magnesium, one magnesium here, one magnesium there. I'm balanced. Chlorine. Chlorine is not balanced because I have one chlorine here and I have two chlorines in there. So what I need to do is just put 2 next to the HCl. And if I do so, then the number of hydrogens here are 2 hydrogen atoms. I have 2 hydrogen atoms in there, so I'm fine. So this is going to be a balanced equation as well. Let's have more examples in there. You guys, if you go to eCampus, there is an extra problem practice that I posted for balancing chemical equations together with its key. Go ahead and do it. This is not a homework, but it is extra practice in there. It does have the key as well. So silicon, I'm starting with a silicon. Silicon is balanced. And then chlorine. I have 4 chlorines in the reactants and I have one chlorine in the product. So I'm just going to go ahead and balance that and put 4 in front of the HCl. Now I'm going to balance the hydrogen. So I have 4 hydrogens here. This is 2 hydrogens. So I'm just going to go ahead and put 2 there. So now the number of hydrogens are balanced. And finally, I have oxygen. So oxygen, I have 2 oxygens. This is 2 oxygens. So it is balanced. Please, guys, pay attention to count all the atoms in the products. So if you have oxygen here, oxygen there, you have to count them all and make sure that the number of atoms in the reactants remain the same as the number of atoms in the product. This is the law of conservation of matter. Um, okay, so here I'm having gold sulfide. Remember, when you name this, gold is a transition metal. So if it's a transition metal, you need to use Roman numeral in there, and the 3 represents the charge of the gold. So I have 2 gold atoms in there. So this is gold. I have 2 gold atoms, so I'm just gonna go over here and say, okay, I need 2. And then I look at the sulfur. I have 3 sulfur in there, so that is gonna be 3. And then the last thing is the hydrogen. I have 6 hydrogens in there, so I would need 6 hydrogens in my reactants. To name the second one, this is mercury. It's mercury 2 and it is a hydroxide. Mercury is a transition element, right? So Mercury here is 2 plus, and the OH is 1 minus. So the charges need to balance out, and this is why this one is Mercury too. So Mercury is a 3. It's a 3 atoms in the product. So I need to put the 3 over there. And then here's the thing, you guys. Whenever you have a polyatom, if you have a polyatom, then balance it as a whole. Balance it as a polyatom. So see, I look at the PO4 as a PO4 molecule and not as a P and 4 oxygens. It's easier. Same thing for because if you see that the polyatom remains a polyatom in the product, just balance it as a polyatom. It's different than this OH in there. I mean, I'm starting with an OH as a polyatom, but that is basically decomposed into hydrogens and oxygens. So the OH did not remain as a polyatom, but the PO4 did. So if it did, just balance it as it is. So I have PO4. This is 2 molecules of PO4. So I'm just gonna go ahead and balance that as 2 in there. So now I'm done balancing the PO4. I am done balancing the mercury. I still have to balance the oxygens and the hydrogens. So let's balance the hydrogen in there. Let's see. We have 6 hydrogens here, right? And we have, if you take a look how many hydrogens I have here, I have 6 as well, because it's 2 hydrogens multiplied by 3. So this is 6. So I have 6 hydrogens in here and I have 6 hydrogens in there. So that is going to be a total of 12 hydrogens. So I have a total of 12 hydrogens. So if it's a 12 hydrogens, then definitely I would need to make it a 12 on the side. So that is going to be a 6 in there. It's going to be a 6. So it's going to be 12. And then I look at the oxygen. In most of the cases, if you balance the hydrogens, the oxygens will be balanced in most of the cases, not in all of the cases. So here I have 6 oxygens. Here I do have 6 oxygens as well. It's 2 oxygens multiplied by 3. So this 3 belongs to every single element in the molecule. So if I want to look at it, you know that I do have 3 atoms of mercury, and then I do have 6 molecules of OH. In other words, I have 6 atoms of oxygen and I have 6 atoms of hydrogen, okay, or 6 molecules of the polyatom OH. Another example, vanadium oxide, we're reacting it with HCl, you guys. So start by balancing the V first. The V is 2, so we're going to go ahead and put 2 in there. And then after balancing the V, balance the chlorine. The chlorine is 6, right? So the chlorine is 6. So we're going to go ahead and put 6 in front of the chlorine. And then balance the hydrogen in there. I have 6 hydrogens. So that is going to be 3. And then look at the oxygen. I do have 5 oxygens here, right? 5 oxygens total. This is it, 5 oxygen. So here I have 2 oxygens and 3 oxygens. This is a 5 oxygen in there, so I am good. Okay, so HCl4. Okay, this is the perchloric acid. I am reacting it with remember, this is 2 nonmetals. So if I want to name this, this is going to be tetraphosphorus, and it's a deca oxide. Use of prefixes with 2 nonmetals in there. So I am starting with chlorine. So let's balance the chlorine in here. So I have a chlorine. Chlorine is not balanced, so I'm just going to go ahead and put 2 there. After I balance the chlorine, I'm just going to go ahead and balance the phosphorus. So I do have, notice, it is PO4, right? I don't have any polyatoms in there. So phosphorus changed into a P. Okay, I don't look at the PO4, I look at the PP. This is how I do it. So the P is 4 atoms, so that needs to be 4. So we're going to go ahead and put 4 in there. Okay, So now we're done from the chlorine, we're done from the phosphorus. We still have the hydrogen and the oxygen. So we're going to balance the hydrogen first. In here, I do have 12 hydrogens, right? And in here, I have two hydrogens. So I need to multiply this by 6. I need to multiply this by 6 in order to get 12 hydrogens in there. So I'm going to multiply by 6. And if you might multiply by 6 in there, then that is going to end up being 12 hydrogens. Um, I do have over here 12 hydrogens as well. So if I keep the 4 in there, that is 12 hydrogens. After I do the 12 hydrogens in there, now I need to balance the oxygen. So the number of hydrogens are balanced. The number of chlorine is not balanced. So before doing the oxygen, balance the chlorine now because we shifted the number of chlorines. I have 12 chlorines in here, so I would need to multiply by 6 in there so that it is 12 chlorines. So this is what I have so far. I have 12 chlorines. I do have 12 hydrogens, right? I do have 4p over here, and I do have 12 hydrogens in there. With respect to the number of the oxygens, okay, so for the number of the oxygens, if I want to go ahead and calculate the number of oxygens, I have 12 times 4, so that is 48 oxygens for the HClO4. And then for the PO or P4O10, I have 10 oxygens in there. Okay, you add those to each other. This is the total number of oxygens in the reactants. And then you look at the products in there and you see, okay, I have 16 oxygens in the product and I do have 42 oxygens in the reactants. So the number of oxygens is the same. 58 oxygens here, 58 oxygens there. So the oxygen is balanced. More examples, calcium chloride and sodium phosphate. So see, the phosphate remained phosphate. So let's balance it as a phosphate group in there. So look at the phosphate here. You look at the phosphate there, you guys, and say, okay, this is two molecules of phosphate. So this is going to be 2. For the calcium, calcium is a 3 over in this side. So it's going to be 3. And then for the chlorine, let's see, for the chlorine, I have 6 chlorines. So I do have 6 chlorines in there. So the chlorine that I need for the product is 6 atoms of the chlorine. And then that will balance the sodium, which is going to be 6 as well. Number of oxygens, as long as the phosphorus oxide is the source of the oxygen. So if the I'm sorry, the phosphate, not the phosphorus oxide. So the phosphate is the source of oxygen. So if the phosphate is balanced, then the number of oxygens are balanced. Okay. Iron sulfide. So this is iron 2 sulfide. So if I want to name this is iron 2 sulfide. Why? Because the sulfur is 2 negative, so the iron has to be plus 2. So it's iron 2 sulfide. Sulfur is a mono atom. It is a one atom, so the ending is going to be an ID. So here, what I am doing is I am reacting FeS, so I'm just actually burning the iron sulfide in presence of oxygen and getting iron oxide and sulfur dioxide. Okay, start by balancing the iron first. So I have iron here. I have 2 atoms of iron, so that is going to be 2. Okay. And then balance the sulfur. I have 2 sulfurs in the reactants. So I need to balance the sulfur in there and say, okay, this is 2 sulfur there. I'm done with the iron and the sulfur. Actually, I just have the oxygen. So at this point, what I do is I count the oxygens in the product and make sure that the reactant is the same. So here I do have 4 plus 3, 7, right? 7 is odd, you guys. 7 is odd. So whenever you are faced with an odd number, this is what you're going to do. You put that number on, I know that I need 7, right? You cannot put 7 there. because it's 7 molecules of 7 atoms of oxygen that you need. So what I do is over here, if I put it like that, it's going to be 14. I don't want 14. I want 7. So I want half of the 14. Okay. So this means that I'm just going to go ahead and do it like this, 7 over 2. But when balancing chemical equations, you guys, we don't put fractions. We cannot put fractions. So that 7 over 2 cannot stay like this. I need to get rid of the denominator. I need to get rid of the 2. So what we do here is that we go ahead and multiply the whole thing, all of this equation. We go ahead and we multiply that by 2. Okay, so if we multiply this by 2, then 2 plus 2, this is equal to 4. Okay, now we're going to end up having a balanced chemical equation. And then I can simply take out the 2's in there. So that is going to be 7. You need to get rid of the 2. And then that is going to be 2. And that is going to be 4. So this is the complete balanced equation. After you do this, we're going to go ahead and double check the balancing of our chemical equation. And that is 4 atoms of iron. This is 4 atoms of iron. I have 4 atoms of sulfur. I have 4 atoms of sulfur. And then I do have over here 14 oxygens, and this is going to be 6 plus 8. So it's going to be 14 oxygens in there. This is a similar example. I have nitrogen. So you start by balancing the nitrogen. I need to put 2 in here, so this is going to be 2. And then I am left just with the hydrogens and oxygens in there. Let's balance the hydrogen before the oxygen. So I do have 2 hydrogen here, 2 hydrogen there. I'm good. So I'm only left with oxygen. So I'm going to count the number of oxygens that I have in my product and make sure that it's the same in my reactants. So the hydrogens that I have in my product are 6 hydrogens, right? So the 6 oxygens, I'm sorry. So this is 6 oxygens in there. So I'm going to count the number of oxygens in my product, not hydrogens. So this is 6 oxygens here. Water contains 1 oxygen, right? So I need 5 for this one here. So I need half of the 10. I cannot put 5 like this because this is 10. So I need half of the 10. So I'm going to get rid of the denominator by simply multiplying by 2. And my answer is going to be 2 nitrogens, 5 oxygens, 2 water, and then 4 nitric acid.